So the question is, I'll keep on switching between you and Rohan when I'm asking questions. So let's start with Arushi. Arushi, what do you think is an atom?
The building block for everything.
The building blocks of everything. Okay, that is a good answer. In fact, a very good definition used for atom. Rohan, anything more you like to add to it?
Not much. Maybe that it's composed of protons, electrons, and neutrons.
Okay, very good, very good. So let's build up from here only. So when we say atom, undoubtedly, when you consider they are the building blocks, right? You are completely right about this part. Now let's think what Rohan has also added to this. So suppose there is a wall, okay, and the wall is made up of bricks. Now if we consider what Rohan has said, each brick is also made up of some subparts, say electron, proton, neutron, right? Rohan, that's what you meant?
Yep.
Now if that is the case, Arushi, then why did we say that atom is the building block and not the electron, proton, or neutron?
I'm pretty sure that they're the building blocks of all life and not everything. So I could have phrased that better.
Okay. Okay. So let me put it in a different way. Let me ask the question in a different way. So, okay, why it is having so much of light? Yes, now it is fine. So let's think like this, Rohan. If we consider as the building block, would this layer be called a building block? Or would this single brick be called as a building block? Or should this electron be called as the building block?
I would say one of the bricks.
One of the bricks. So still we are with bricks, but not electrons yet. Right? Okay.
Correct.
So the idea behind saying them as building block is we want them as, so atom, that refers to smallest unit of matter, right? That's why we are calling it the building block. But there is something which we miss every time. And what is that particular thing? That particular thing is capable of independent existence. That's why it is called the building block. Okay. Now, if I say there is electron, Arushi, can you find any case in which one electron is independently existing without any other atom surrounding it?
No.
No. Rohan, have you considered any case in your owners in which one electron is independently existing?
No, maybe
No.
in a cathode ray. I don't know.
But again, that just starts from one point and it goes to the other point, right? Like if I say that, okay, let's get a kind of setup in which we are able to extract all the cathode rays and we are able to preserve that thing as collection of electrons, like is that kind of a possibility?
I don't think so.
So that is not possible because we can't have a single electron as a independently existing unit. Okay. So that's the reason why atoms are called as the building block, because they are capable of independent existence also. Now, if I am telling you about electron, maybe maybe towards the end of this course of AP chemistry, we will get to know about something known as ammoniated electrons. I'm not very sure whether we will get in its detail or not, but there can be a thing like ammoniated electron. Arushi, any guesses? What does that mean?
I don't know.
No. Rohan, what would you guess it for?
I actually have no clue either.
Okay, so ammonia is the equivalent of water, something like water. So water is H2O, right? So suppose you replace oxygen with nitrogen, and then of course to balance the valencies, you need this kind of thing, which we generally say NH3. So this is called ammonia. And uh, if electron is surrounded by ammonia, then it is quite stable. Okay. So if many ammonia molecules are able to surround, one electron, then it is stable. And in that case, it is called ammoniated electron. Again, the point I'm trying to refer is independent existence of electron is not possible. That's the main point. Okay. So Rohan, Arushi, are we on same page now? Why
Yeah.
atoms are called what they are called?
Yes.
Okay, great. Let's move to the second most trickiest term, which is molecule. So let's go with this term. Rohan, what is molecule?
I would say that it's just a combination of atoms in a whole number ratio.
Okay, okay. Fine, good. Arushi, what would you say?
Probably the same thing.
Mm-hmm. So this part more or less is easy to understand. So it is group of atoms, right? So that's what we generally feel a molecule to be. It is a group of atoms. Then at times you will also see there is something like ions, right? There are ions also. So Arushi, what is ion or ions?
When you have more neutrons than protons and electrons in an atom
Mm,
or in a
okay,
molecule.
that might not be the case, but uh, it is close in a way. Maybe not the exact definition. Rohan, what would you go for?
Isn't it when a molecule or an element has a charge?
Okay, good. So atom or molecule with some charge. Okay. So Arushi, what you said, it might be true in one case, might not be true in other, but the charge thing is is the definition. So again, say we have Na and we have maybe HNO3. So this thing should be called as atom, and because this is a collection of atom, it should be called as molecule. The moment you make it Na plus, now it can't be called as atom. What is it called as? It is called ion. In fact, Rohan, what is positive ion known as?
Is it anion?
It is cation.
Ah,
Okay. And Arushi, what do you think can be the two ions we get from this HNO3 molecule? You might be
Um,
aware.
H, H and then NO3.
Okay. But if they have
Oh,
to be ions,
H positive, NO3 negative.
okay, very good. That's a good guess. So H plus and NO3 minus, and yes, it is a cation, and this is called anion. Okay. So the basic things first, we have dealt with atom, molecule, and ion, right? Now let's come to another part, which is element versus compound. Element versus compound. Rohan, where we see element as?
I don't really know, sir.
Okay, no issue. Arushi, we frequently use this term element. So what it refers to?
Element is a mixture of the same atom, and then
Okay.
compound of different atoms.
Okay, very good, very good. So we can say it is matter consisting only of one kind of atoms. Okay, so it might be one atom, it might be many atoms. So you are right about this. You can say sodium is an element. You can also say P4 is an element. You can also say S8 is an element. C60 is also an element. All these are elements. You're right. Okay. And what you said about compound, that is also true. It is group, or what should I say, consisting more than one kind of atoms. So if I have HNO3, if I have CO2, there is say SO2, SO3. So there are more than one kind of atoms, right? More than one kind of element. So you can say in terms of atoms or elements also. So atoms or element. So then we go with this definition. Rohan, this definition is fine?
Yeah.
Okay, great. Now let's look at the tricky part. Arushi, can we say element is always atom?
No.
No. So the question would be like this: can element be molecular? What would you say? Can element be molecular? Like, can it be in form of molecules?
I think so.
Yes, you are right. So P4, the things which we wrote above, they all are in terms of molecule, right? So Rohan, about compounds, can a compound be atomic?
I don't think so,
Why?
because atomic is referring to like one, right? And a compound is many, right?
Okay,
So,
good. So at least it must have two atoms, because only then it would have two different kind of atoms as a possibility, like CO, NO, right? Something like this we will have, only then we can say that, okay, yes, it is a compound. So if we say, can a compound be atomic? The answer is certainly no. Okay, great. So I'm going to give you some random things. You have to classify them. So whether they are atom molecules or whether they are element compounds. Okay. So I'm giving you, you can tell me. So I'll start with P4, CO2, SO3, HNO3, Na, and of course we can have something like H2SO4. Fine. And we can also include S8, and I think to close we will have CO3 2 minus. Right. So the left portion belongs to Rohan. Rohan, let's start. So P4, atom molecule.
Atom
Okay. One atom or group of atoms?
group.
So if it is a group, then it is
Oh, it's molecule.
it's a molecule. Element compound.
Element, because it's just one.
Okay, good.
Yeah, okay.
How about CO2? Atom, molecule.
Molecule.
Good. Element, compound.
Compound.
Very good. SO3.
Molecule.
Nice. And
Compound.
good. S8.
Molecule.
And
Element.
element. Excellent. Arushi, your turn now.
Molecule, compound,
Molecule and compound, right?
atom, element,
Very good.
molecule, compound,
Okay.
molecule, compound.
Molecule, compound, or I would say ion, right?
Ion.
Yeah. Okay, very good. So I think we now understand the basic terms of chemistry, right? Atom, molecule, element, and compound. So these things we will be dealing most frequently with. So it is very important to get their basic understanding. Now let's try to explore a formal definition of chemistry. Okay. Rohan, would you like to try? What is chemistry actually? What we are going to study for next 7-8 months?
The study of chemicals.
Okay, study of chemicals. Fine. Arushi, anything to add? Sorry.
No.
Okay. So, Rohan, when we say chemicals, do we try to study about their properties more, or do we try to study about their reactions more?
I would assume both equally.
Both equally. So what we can say, study of chemicals and their reactions. Okay. So that's the thing. And chemicals, we already have covered this part for now. They essentially would be either atom molecules or element compound in some form of or other. They are the chemicals what you are trying to refer. The important thing is reaction. So that's the tricky part. What qualifies as a reaction? What is considered as a reaction? That's what we want to know, right? So, Arushi, what do you think is a reaction?
When two elements are combined and then they have a change in properties.
Okay, good, good. So that is certainly one kind of reaction. Perhaps you are talking about combination reaction, and that makes perfect sense. Rohan, a more generic definition of reaction?
When two chemicals react with each other.
Okay, so yes, that is fine. Like literally, the meaning of reaction is react the two things reacting with each other. However, if we try to go something deeper, we will say in a way it is two. So I'll say one or more chemicals converting to some other, again one or more chemicals. Like if you technically see all around, that's what we meant by reactions. So you name any reaction and you would find that okay, this very self-made definition, very in a way layman's definition is working out, right? So if we have say CaCO3, we have CaCO3 and we try to heat it, it dissociates into CaO and CO2, right? So we have one compound which dissociated into two other compounds. We had one chemical which dissociated into two chemicals, right? What Arushi said in beginning, Na plus O2 going to Na2O. We had two elements combining to form one particular compound, right? So essentially the things are undergoing some kind of change, and that change in chemistry is addressed as chemical reaction, right? So that's the thing. Of course, we will be dealing about many kind of reaction, like this example I have given you. So this example is a classical case of decomposition reaction, because as we see, the CaCO3 is decomposing. So this is called decomposition reaction. This example, of course, they are not decomposing, they are combining with each other. So it is called combination reaction. Okay. So we will try to study the kind of reactions, types of reaction as we go ahead, not in like the demo class, certainly. Then there is the terms which are very confusing and which we need to get hold of. Uh, First thing first, I think we should go with atomic number. Okay, that's the simple thing actually. And then there is mass number versus atomic weight. I think with this we can do some serious discussion. Arushi, where do you see atomic number as?
It's on the top right corner in the on the periodic table, but it's
Yes.
always it's the number of protons and electrons in an element.
Okay, very good, very good. So the first part is always true. Second part is along with the condition. So it is, of course, number of protons. Okay, you are very right. In an element, and equals number of electron if element is neutral. So that's the main thing, right? So why I'm saying that, let's discuss it right away. Rohan, any guesses what is the atomic number for sodium?
For sodium, 12,
Very close, it is 11.
11.
Yeah, very close it was. So for sodium it is 11. So when we say atomic number is 11, what does that mean? That if you go inside the sodium atom, you will find 11 electrons as well as 11 protons. But Arushi, suppose I say Na plus is there. No, what changes? Proton changes or electron changes?
Electrons.
Electrons change, right? So now we have 11 protons, but the number of electron goes to 10, right? So electrons may be equal, maybe more, maybe less, depending upon the species is neutral or charged. Rohan, this is fine now?
Yeah.
Okay, great. So now let's see. So this was about atomic number, the simple thing. What is mass number, Rohan?
Mass number.
Mm-hmm.
Is that the number of protons and neutrons?
Very good. So it is number of protons and neutrons. That is perfect. Very nice. Arushi, you might have heard, atomic weight term also, right? In fact, this mass number term is not very popular. The popular term is atomic weight. So, like, are they the same things? Are they different? What do you think?
I'm pretty sure they're different because I think because electrons weigh a little bit less than protons do. So I think when you talk about atomic weight, it's more specific to the number than just the count of how many there are.
Very good. Very good. So let me show you something. Right. This is a good example. I'll put a snippet. Yes, here we have atomic weight or atomic mass, essentially the same thing, right? So let's have a look at for carbon, hydrogen, oxygen, chlorine, for everything they are saying, right? Sorry. So when you say mass number, and as Rohan put it correctly, mass number is number of protons and neutrons, and you will always find it to be a whole number. It is always a whole number. It is never a fraction, a decimal thing, nothing like that. Okay. The moment we go in domain of atomic weight, this whole number concept is gone. You look at carbon, it is 12.011. You go at hydrogen, 1.00, 15.99, 35.45. So these kind of things start happening, right? So certainly Arushi identified correctly that yes, there is some sort of difference. That's why there are two terms. If there was no difference, why we would be introducing two terms? But let's try to explore what that difference is and why that difference is, right? So, Rohan, what do you think is the difference between atomic weight and mass number, and why they are not exactly same?
I think it's because atomic weight takes into account different mass numbers because sometimes the same element has different number of protons.
Excellent, excellent. Not the protons, just
Oh,
this word is
neutron, my
from
bad.
neutron.
Neutron, my bad.
Yes. Otherwise, the thing makes very good sense. So Arushi, let's try to explain what Rohan said as this. Suppose you say hydrogen, right? When you say hydrogen, only one thing is fixed, that the number of protons is one, right?
Yeah.
But the number of neutrons, that no does not know any bound. That can be 0, that can be 1, that can be 2. Okay. And if you go with this, you will have different mass numbers. Like here we have 1, here 2, here 3. In fact, they all have different names also. This is called protium, and this is represented as 1H1. 1H1. You see this species, this is called deuterium, and it is 1H2. And of course, then we have tritium, which is 1H3 also, right? And Rohan, what they are called with respect to each other? They are
Isotopes.
isotopes. Very nice. So they are isotopes, elements having same atomic number but different mass number. Arushi, that is fine, with same
Yes.
atomic number but different mass number, and that difference is due to difference is due to number of neutrons. Like that's the thing which is causing the difference. So the thing is, in our mind, at times we can have perception that okay, whenever I say hydrogen, it means only this. No, but in nature it is not like this. What it is, that suppose around 98% of hydrogen is in this form. Okay. But maybe 0.5% is in form of like this thing also, 3, 1 and H, and maybe 1.5% of hydrogen is in form of 2, 1H. Now please do a very little calculation and give me the average atomic weight of hydrogen based on this. Please quickly do it. You need to use calculators and a little bit of maths. Please try it and tell me what is the atomic weight of hydrogen if this composition is given to you. Try it out, try it out. Rohan, Arushi, whenever we have an answer, please let me know. Okay. Sorry. Rohan, are we getting any number? Arushi, are we close to some number?
No, I don't
No.
remember how to do.
Okay, no issue. No issue. Rohan, are you there?
Yes, I'm here, but unfortunately, all of the right side I cannot see because there's a big pop-up in the middle of my screen and I cannot close it out because the mouse is also frozen.
Oh,
So
okay,
I
okay,
can
okay.
only see 98%, 0.5%, and 1.5%.
But on the right side, you are not able to see. Now, is it somewhat more visible?
Yeah, it is.
Okay, fine. So we can do calculation in this part. So Rohan, were you able to do some calculation or at least know the method how to go around this?
I'm pretty sure you multiplied the mass
Mhm.
by the percentage for each one,
Very nice, very nice.
and then you add them all up.
Good. That's a good method. Good. So let us understand in terms of what Rohan said, as well as in somewhat more general manner.
Can I
So
ask a
first,
question?
yeah, go ahead.
I did that actually, but I wasn't 100% sure it was right, and I got 6.5.
Okay, then it is a calculation mistake only. Conceptually, you are right.
Okay.
Conceptually, you did good. There was nothing wrong in that. Okay. So let's try it. So let's go ahead directly with 98%. Now, what does 98% means? It means 98 by 100, right? And let's multiply it with 1. Then we go with 0.5%. Again, what 0.5% means? 0.5 by 100, multiply it with 3, right? Let's go with 1.5%, 1.5 by 100, and this is the thing. Right, Rohan? This much is visible, or should I write even on more left? Like,
It's now visible, but before I could only see the left two.
okay, okay, great. So this is the thing. Now, if we add them up, So if we quickly try to add them up, I think we will get somewhere. This is 0.98, and how much is this? 0.015, something like this, I think. And this is 3 divided by this, so that is like 0.30. Right? So we will be having something like this. So 0.03. So 0.45, and I think it will give you 1.025, right? Something like this will come. So Arushi, where was the mistake?
I didn't divide by 100.
Okay. So that part was somewhere remaining. That's why conceptually you were right. And calculation mistakes we need to see where we can avoid, right? So that's the logic why we every time see them in decimal form and not in the form of whole numbers. And in a more general way, if we try to see, we can say, okay, we have a group of hydrogen atoms, and in that hydrogen atom group, 98 atoms are weighing, say, 1 unit. Okay, only so maybe 100 is not a good example. Let's take 200 atoms. So out of 200 atoms, around 196 is weighing 1 unit. One atom is weighing 3 units, and two atoms are weighing how much? 2 units, not two atoms, 3 atoms. Why I have chosen this kind of situation? Because if you see, it means 98% has weight of 1, 0.5% has weight of 3, and 1.5% has weight of 2. So it is exactly the situation which we had above. And now just the general method, that what you need to do, 98 into 1, sorry, not 98. How many we have for 1? 196. 196 into 1, 1 into 3, and 3 into 2, divided by how many total atoms you have? 196 plus 1 plus 3. Again, you will get the exactly same number, 1.025. Okay. So this is like what actually happens. And the above thing is like how the formula works. You simply multiply the percentage with the atomic weight, and that gives you the answer. In fact, when we start doing it more technically, you will say this percentage refers to, this is something known as relative abundance. This term will come into picture. It is called relative abundance. So that's pretty much about these 2-3 terms. Now let's move towards, so we will keep a very short demo, maybe 15 minutes more. Okay, you will get a fair idea how the things work, I think, right? And based on that, you can make your decision, I guess. So let's try to do one last concept before we conclude today's lecture. It is mole, the concept of mole. Arushi, have you heard this term somewhere, sometime?
Yeah.
A very pretty number or a very cumbersome
No.
thing? No? Rohan, what is this number referring to?
Isn't it the, what's it called? Atomic number in grams? Isn't that a mole?
Atomic number in grams. Related to it for sure. But let's see exactly how it is related. So let's first of all simplify it as much as we can, right? So let's say we have two, maybe two things are there. We can simply call it a pair, right? If there are 12 things, we call them a dozen. Now chemists are weird, and they found out 6.022, 10 to the power 23 things, and they called this quantity as a mole. So first of all, let's just acknowledge that mole is nothing but a unit of measurement. Okay. So if we go around in a hypothetical place and we see that, okay, there are 6.022 into 10 to the power 23 people standing there. So that means 1 mole people are standing. Okay. If you find that, okay, in a particular hypothetical country, these many currency notes are there. So you will say 1 mole currency notes. Okay. So the idea is it is as simple as what we call a pair or as simple as dozen, right? It's just that the quantity it is dealing with is huge, right? So 10 to the power 23, it is like very, very big number. So how it is related with what Rohan said, let's try to discover that part also. So when we say 1U, right? 1U or Rohan, I think what you meant was 1 AMU, something known as atomic mass unit, right? So it is actually related to grams in a way. So Arushi, are you aware how much is 1 atomic mass unit in terms of grams? A rough idea, any close thing would work? Not really. Okay. Rohan?
Is also 6.2 times 10 to the 23rd power.
Not really related to it, but not this. Like some relation is there, but not exact similarity.
Okay.
Yeah. Rohan, would you like to try in terms of grams?
No, sir.
No? Like you were close when you said the definition. You were pretty close actually. So if we go with the exact measurement, so 1 AMU is actually equal to around 1.67 10 to the power of negative 24 grams. Okay. So if we actually do the calculations, the measurements, I'll not say calculations, you say you are doing an experiment and you measured out how much is the actual weight. Okay. So 1 AMU, 1 atomic mass unit, is equal to this much grams. So let's try to understand it in terms of hydrogen. So what is hydrogen? Generally, when we have hydrogen atom, we have 1 proton and 1 electron, right? That is hydrogen. Because in most cases, hydrogen atom is not having a neutron. We are dealing with protium right now. So if we try to go with the weight, so Arushi, any guesses about one is the weight of 1 proton? Any random guess?
A little bit more than one, like 1.00 something.
Okay. So actually, that little bit more things come with neutron, but let's get the exact thing. So it is 1.672 10 to the power of minus 24 grams. When we come to electron, Rohan, does electron weigh more than proton or less than proton?
It's actually negligible, right?
Right, very good. It is very negligible and it is around 9.1 10 to the power of minus 28 grams, like 10,000 times lower weight it has as compared to a proton, right? So when we add them up, we don't really say that, okay, the weight due to electron has been significant. We simply say, okay, fine, it is approximately still the same, what we essentially wrote. And this particular thing can be called as 1U, or in very simple terms, it is approximately the weight of 1 hydrogen atom. Okay. That is fine now. Now, let's say scientists were curious on a number which gives you some good number in grams. So what I mean to say is, if you have one atom of hydrogen, it is weighing 1 U, which means it is weighing 1.67, 10 to the power of minus 24 grams, right? Suppose I take X atoms of hydrogen. If I have X atoms, so Arushi, if one atom weighs 1 U, what would be the weight of X atoms?
XU.
It would be XU. Very good. And Rohan, what we already have understood U as? U is equal to what?
The mass of one hydrogen atom.
Yes. And in terms of gram, we can put it like this, right?
I cannot see that, sir.
Oh, okay. Let's bring it on right now. Now is it visible?
Yes.
Okay, great. So what we are interesting at this point is to find out X such that this weight becomes 1 gram. So I want to find X number of hydrogens such that their weight, which is equal to this, becomes equal to 1 gram. Okay. So if you do that, the simple thing is it comes around 1 divided by 1.67, 10 to the power of minus 24. What does that mean? Sorry. That means you have 10 to the power of 24 divided by 1.67. And if you use calculator, some kind of calculation, this number approximately gives you 10 to the power of 23. Okay. So that's where the initial definition which Rohan stated and Arushi, where you tried to relate, they come into picture. So actually, what we can say is that look, weight of one hydrogen atom was 1 U, right? But if you take weight of 1 mole hydrogen atom, now it becomes 1 gram. Okay. And when we say mole, that is referring to how much? 6.022 10 to the power of 23 atoms. Okay. So Rohan, if we say you take weight of 1 oxygen atom, we have 1 oxygen atom that weighs 16 U. But if you take weight of 1 mole oxygen atoms, Arushi, what would that be equal to?
16 times 6.022 times 10 to the 23rd.
Which will give you 16 grams.
Okay.
Okay. So what you said is perfect. It is 16 U times 6.022 10 to the power 23, right? What is this U? This U will see 1.67 10 to the power of minus 24. And if you multiply each other, they become 1. Okay. So eventually, so anything which you see in U, if you take 1 mole of that thing, it converts into gram. And that's how these numbers are. They are basically multiplicative inverse of each other. They just cancel out each other. They become 1. Okay. Rohan, Arushi, is this part clear?
Yes.
Okay. Okay, great, great. So that's the beauty of this concept of mole, that we at times we keep on wondering why this particular bad number has been chosen, why we could not have gone with, say, simply 10 to the power of 10, a very good number, right? Why we chose particularly 10 to the power of 23, which seems like a prime number, no reason to go to such a number. And then why this random factor of 6.022? So this is not random. The thing is, again, I will say AMU and mole are multiplicative inverse of each other. Okay. So that's the thing, right? So in today's brief introduction, I think I haven't used any term which you were completely unaware of, right? But still we tried to get some basic understanding, so that if the term comes, we are exactly feeling what does that mean, right? We are not just superficially looking that, okay, 1 mole means this much, why it means this much. Okay, we know that, okay, you convert u into gram, but why you do that, right? We should be sure that whether the species given to us constitutes as compound, or should we call it element? Is it an atom or is it a molecule, right? So that's what we have tried to build in this lecture. And as you will see, we try to do things in this manner only, right? One thing which I try to make very clear is, like, we help you prepare in your main AP exam, right? So why I'm saying is because right now you two students are there. Around, when this batch saturates, we will be having around 7-8 students. Now every school works at a different pace, right? I'll definitely try to help each one of you individually also, but practically it is not possible that, okay, we follow one particular order, right? We always follow what is given, is given in college board uh, sequence, and we exactly do that. And one thing I assure you is that we will cover everything in this much detail like we did today. So I think based on this, you can make some kind of decision and you can let me know. Okay.
I have a couple of questions.
Yes, sure. Let me close the recording and then you are free to ask.